Okay, good morning. Good morning, everyone. Thanks for the organizers and all of you for this opportunity to show you some of our work in Mexico. This time, it's going to be similar talk as some of you have seen it in Reading. And of course, the work that is being done and presented here is not only my own, but also including the effort and collaboration from colleagues like Pedro from CIGOM, Nicolás from IFREMER, Héctor from the University of Baja California, Guillermo and Bernardo, and Carlos, another Carlos, and Rodney, and them from CIGOM. And this is the WAVES group. Oops. So in this presentation, I would like to tell you about the efforts that we have been doing to establish a buoy network. This is under National Research Council project supported in conjunction with the Ministry of Energy in Mexico. We managed to develop and build enhanced spar buoys to study the ocean surface wave dynamics. In fact, this is a kind of a copy of ASIS buoy from the Miami group, but we have our own electronics designed. We focus in the air-sea interaction and surface currents, since we would like to know better processes in the upper ocean and lower atmosphere. And in this particular talk, I'll be showing some things that we have been doing to explore a different point of view to analyze the surface stress, especially when we have only single peak spectra. And also, in another aspect, trying to understand the influence of swell on wind sea development. So to start with, I'd like to tell you, can we move this? Yes. I'd like to tell you about the buoy that we built. As I mentioned, is the original design by Graber and colleagues. And this type of buoys have been successfully built and deployed in several experiments, like one in Mexico that we did in the Gulf of Tehuantepec in 2005, and some others recent under the ITOP project, like Collins and colleagues and Drennan and others, especially for hurricane conditions and high winds. So this type of buoys are, as I said, enhanced spar buoys with our own electronics and several other sensors. For this particular work, we focus on the sensors like sonic anemometer that was sampling at 100 Hertz. We also have an array of 6 capacitance wave staffs sampling at 20 Hertz, and the electronic unit with 6 degrees of freedom motion sensors sampling at 100 Hertz. There are other sensors, like I mentioned, a met station, CO2 concentration in air and water, and so on. And we have still the plan to include CO2 sensors, video cameras, but these are only under plans. The essential point here is that we manage and we would like to have more simultaneous measurement, which are really needed. As a result of the experiment that we did in the Gulf of Tehuantepec, we can recognize, and has been already mentioned, that the drag coefficient is not just a function of wind speed. So we have a lot of variability, and in some cases, some results from some experiments do not match results from others. And we believe that it is because this scatter is an influence of other processes apart of the wind speed. Besides, as it has already been mentioned, the wind stress not always have the direction of the main wind. And this is an example of our results in the Gulf of Tehuantepec, showing the relative direction of wind stress in comparison to the mean wind as a function of wind speed. So we really wanted to understand better those processes. And this is the sketch of the sites where we deploy the buoys near Ensenada as a trial sea site, and these 3 positions in the Gulf of Mexico. Under this project that I mentioned before, supported by National Research Council and the Ministry of Energy. At the end, for this particular work, I'm going to tell you about results from these 3 sites. The one in Todos Santos Islands, where we deploy the 3 buoys as sea trials before sending them to the Gulf of Mexico. And these other 2 stations, called Perdido and Alacranes Reef, that were the sites for the other, for 2 of the buoys. The operations were for these 3 buoys, as I said, in Todos Santos Island, the sea trials. The 3 of them were for a couple of months or so before going to the Gulf of Mexico, and the one in Perdido operated from July to sometime in July 2018 to sometime in 2019. And we had good measurements from, we are showing results from measurements in the Alacranes Reef obtained during April and October 2019. So these are the sites more specific of those 3 locations. Just as an example of our results, this is a time series of the wind speed and the significant wave height acquired by BOM 1 at Perdido station. And we can see here that conditions were kind of normal, nothing drastic, and we managed to observe several atmospheric fronts passing by over the Gulf of Mexico, generating winds up to 15 or 20 meters per second in some conditions. Of course, the waves were also moderate over most of the time, but under those conditions of atmospheric fronts, the significant wave height increased up to 3 or 5 meters. And as you can imagine, the sea states are quite different from the Pacific and the Gulf of Mexico, and, and even within the Gulf of Mexico, we have situations where was a single spectrum as wave conditions, and in some other cases, even double peak, especially when those atmospheric fronts were present. For this particular work, I'm going to focus first as a first aspect, wind stress, to analyze the wind stress under single peak spectra conditions. And another idea of the overall picture of the wind conditions and wave conditions for the 3 locations are these. So with this, we can see and we can stress that there is an important variety of wind and wave conditions in the station that we are getting the data. So to analyze the wind stress, we rather use a system of reference aligned with the wind, and as I mentioned, is under only single peak spectra conditions. And the system of reference is this one, proposed by Grachev and Ferrell, where X is aligned with the main wave propagation. In contrast with other typically reported or used reference system aligned with the wind. We also use the arguments by Buckley and Veron, where the wind can be expressed in these 2 components, and the oscillations can also be decomposed in turbulent part and wave coherent part. Likewise, the wind stress can be decomposed in turbulent term and wave coherent part. So we are interested in the wave coherent part, and it is straightforward obtained from this expression, the wind stress The total wind stress is estimated directly through the Eddy covariance method, and wave coherent stress is estimated through this expression given by Beron et al. And the turbulent part is just the subtraction of the two. We also use a reference normalized wind system, which is not just the wind, is a, as I say, reference normalized wind, where wave characteristics are included, like theta p, which is the wave direction relative to the wind, and the phase velocity. We also consider Hanson and Phillips' idea regarding the conditions of wind C. Whenever this normalized wind is greater than point C, we can consider it as wind C. Otherwise, it's swell, and swell has also these other important characteristics. With this reference wind, we can also detect if the waves are following the wind, or are opposing the wind, or are cross winds. And then one of the main results is the along wave component of the wave coherent stress as a function of the reference wind. So we can see here that the swell conditions are between minus 0.7 and 0.7 approximately, and we can see that there is negative values of wind stress, and what the plot is showing here is that we have negative wind stress under these swell conditions, and this negative wind stress is enhanced with the significant wave height. This is a simple explanation and results, and the paper is already submitted, but for more details, please come along poster 6 by Carlos Villarreal Olavarrieta, which is here. And a second aspect that I would like to mention is that we are trying to understand the swell influence on wind C evolution. And for that, we first select very carefully pure wind conditions under kind of or quasi-stationary conditions of wind pattern. Yeah. These conditions are just thinking on the wind speed should not vary much less than 2.5 meters per second from time to time, and the direction of the wind shouldn't vary neither. So under those conditions, we managed to obtain from the data set, say, pure wind spectrum. And then we analyzed for 4 cases of atmospheric fronts, and these are the characteristics of wind under those atmospheric fronts identified as number 6, number 8, and 9, and 10. And we managed to detect quasi-stationary conditions for the wind all over this period of time, approximately 50 hours from the starting of the atmospheric front. In other cases, in other fronts, the duration of these constant conditions or quasi-stationary conditions are less or variable from 3 to hour 18 or so. And the wave conditions under those atmospheric fronts are these. Of course, the significant wave height varied along the time. The significant wave height is the blue, and also detected the mean wave direction for those conditions. So this is an idea of what the conditions are for these cases where the atmospheric fronts were present. So when we analyze the pure wind C cases, we obtain these growth curves, which is the normalized wave energy, non-dimensional, as a function of the peak frequency, and they match rather well several results from other authors. And if we include the spectra with swell, we plot those results as a function of the same peak frequency, but color-coded with characteristics of the swell. In these colors are the swell direction relative to the wind. So reds are opposing the wind, and blues blues are crosswind and nothing along the wind. But also we managed to calculate so-called swell index, where we can detect the amount of swell within each sea state associated to the non-dimensional energy. What we can see here is that apparently the swell doesn't influence much the wave growth, or yes, the energy, non-dimensional energy from these plots. But intriguingly, if we plot the same results as a function of of fetch, the same characteristics of color-coded, the swell direction relative to the wind is this red, which is opposing swell. Apparently, the opposing swell is inhibiting this wind sea and the total energy of the wind sea spectrum. And the same plot with different color code, which is associated to the swell content, indicates that it is these dots which are swell, and also the swell is have a higher stiffness when it is making this influence over the wind sea evolution. So this is something rather intriguing that still we are trying to understand it, and further analysis is needed. So just to conclude, as final remarks, I'll mention a pilot buoy network supported by National Research Council and Ministry of Energy project. We measure and calculate surface stress with spar buoys. We try to analyze the wind stress from a different point of view to explore and analyze the surface stress. Specifically, wave coherent stress is negative under swell conditions, along and opposite to the wind. And we are trying to understand the swell influence on wind sea and wind sea evolution. And apparently, swell opposing the wind seems to inhibit wind sea growth. Thank you.